And let's test our code and let's see if it works. So we can go ahead and run this cell. And these actually look like real lyrics. In fact, we can run it again. We can see if we get real lyrics as well. And yeah, we get some different lyrics. And of course, we can increase the number of characters here and get even more lyrics. Okay, this is our final problem in this list of problems, and we're finally going to generate text. We're finally going to generate text using all the code we've written so far. This problem is going to combine concepts from this entire series, and we're finally going to use the GPT class that you wrote. We're going to use that exact class. One of the inputs is actually an instance of that class, and we're going to use it to generate text. I took the model that you coded up in the previous problems, the GPT class. I made an instance of that class, and I trained it on a raw data set of all of Drake's songs. So what's being passed into you is actually a model that is specializing in generating Drake songs, since that is the body of text that it learned to model really well during training. And we're finally going to get to write the code that actually generates text from models, these large language models. So it turns out that implementing inference, this idea of using a trained model and actually using its weights to generate new things, is called inference. And it's a bit more complicated than just calling this forward method from the GPT class over and over again. And this is a valuable skill to really understand, because then you could actually download open source models. You could download open source weights from online and implement inference for them on your own, and you actually generate text. And that can be a really fun side project. So, and the reason it's more complicated than just calling forward in a loop is because forward is not outputting like a clear-cut output of what the next token in the sequence should be, right? If we pass in my name is into this model, let's treat the model as a black box. This is our model. And if we actually pass in this sequence, and let's say we know the answer is Bob, and let's say the model has been trained really well, and the model knows that the next word is Bob, but it's not going to give us a clear-cut answer like this, right? That's not what this model outputs. This model outputs a vector of size, vocabulary size, or capital V, where that's the number of tokens that the model was trained on. We have a bunch of numbers, each between 0 and 1, and if we go to the index where Bob is, that's actually going to be like a really high number, maybe like 0.95. So the model is outputting a bunch of probabilities of each possible next token, whether that's a character. In this model, it's actually going to be a character, but it can obviously be a word. It's just some token. So given a bunch of probabilities, how do you actually choose the next token? Because it turns out just taking the highest probability token doesn't necessarily yield the greatest results, and we'll explain why in a bit. The model is only also allowed to read context length number of tokens back into the past, right? As we're generating text, these generations can keep growing and growing and growing. And we're going to need to actually truncate off tokens that are farther back than this threshold at every iteration. And the way that your code will actually be validated is we'll just check to see if the string that GPT is returning back to you, whatever text, actually matches what it should be. So let's try and understand this example. We're given an instance of the GPT class, and that's going to be the model variable. Then we're told how many new characters to generate, and we're given the starting context. So if the model is a black box, this is our model. We go ahead and pass in some sequence of tokens of length capital T. We're going to start off here by just passing in one token, and specifically is 0. And so since we just have one token, we can say that capital T equals 1. And if you look at the vocabulary dictionary, remember, we actually encode our tokens as numbers, right? When we're doing NLP, we can see that 0 is corresponding to the new line token. This is corresponding to the new line token. And that's going to kind of be our start token. That's going to kind of be like a start token to tell the model, hey, start generating text. And in this case, since we train the model on lyrics, you can maybe think of the new line token as say, okay, start generating a new stanza or a new verse or something like that, right? And we actually are going to then get a probability distribution. We're going to pick a token. So we're going to choose choose the next token, and then once we decide that, we're actually going to concatenate it to our original input. So now this will be of length t plus 1. That'll be the size of the input, and then we'll call the model again inside some sort of loop. We'll get the next token, and then this process just continues. So we need to be told how many times to actually generate new characters, and that's this input over here. And of course, as this input grows, right, as we are generating new tokens, appending them back on to the context variable, as we are appending to context and the context is growing, at some point, those tokens from the past, maybe those starting tokens, need to be cut off if the input is getting too long for the model to actually process. So that's our context length. And then again, this is just a dictionary for encoding integers to characters. This is going to be a character level model instead of a word level model, but all the concepts are exactly the same. And although your output, when you actually run the code, when you solve this problem, it's not going to match exactly this just due to computational limits within the browser. I went ahead and ran this model. So I used the solution code for this problem and used your GPT class that you wrote in the previous problems. And this is the output I got for only 60 characters. So you can count this. This is 60 characters. And we can see that it's something that actually resembles like Drake lyrics. So that's pretty cool. So now let's jump into how it works. So this is going to be our general workflow for this generation loop. From the model output at every iteration, we're obviously going to call the forward method of the given model at every iteration using our growing context, which again, we have to remember to truncate if it gets too long. We are going to then get probabilities. However, the output of this model, as the starter code says, has actually been before softmax is applied. So they're not actually between 0 and 1 yet, and we need to actually get those probabilities. So we're going to actually use nn.functional.softmax. And of course, we're going to use the last dimension. So we say something like dim equals -1, so we can make each row actually sum to 1. However, the model's output, before we even apply softmax, the model's output is of shape b by t by v, right? For every single token, at every single time step, we have this vector of size v, all the probabilities. But we've actually been calling this model over and over again inside the loop, and this t has been growing. It starts off with t equals 1, and then t equals 2, and then t equals 3 as we generate the tokens. But each time, we only really care about the next token, right? The next token that's going to come in our sequence. So we only actually care about the last time step here. We don't care about the model's predictions for the previous time steps because we already have the answers, or we've already chosen a token. We've already chosen a token from the probabilities and done our whole sampling thing, which we're about to explain. We've already chosen those tokens. So we just want to actually index the model output at the final time step. So we might do something like, let's say we had the model prediction stored in some kind of variable, the model output. You would actually want to leave batch size the same, but take the last time step. And of course, you want to grab all the vocabulary entries, all the probabilities. So you would leave the vocabulary dimension the same. Then you can apply softmax. And from those probabilities, we're going to do sampling. So let's talk about sampling. So given a bunch of probabilities, one choice is just to keep choosing the highest probability token. Look at the max, look at the index of the max probability, and simply choose that token. However, we're instead going to do something called sampling. Sampling can kind of be likened to drawing marbles from a bag. Let's say there's a bunch of marbles of different colors, and some colors appear more often than others. The ones that appear most often, if you keep repeatedly drawing into the bag, those are going to pop out more often. But occasionally you can still get the lower probability, the lower count marbles. That's exactly what we're going to do here. And there's a function called torch.multinomial that is going to simulate this sampling process. All we have to do is pass in the probabilities, right? So that's after we applied softmax. The number of new essentially drawings that we want to do from this bag of probabilities, that's just 1. And then for reproducibility, so that your test case is not random every time, your test case is output, you need to pass in the generator. Why do we sample? Why are we doing sampling instead of just taking the max probability token? I go into this in more detail in the background video for this problem, but the short answer is if we let the model occasionally choose like the second most likely or the third most likely, we can get a lot more diverse and interesting outputs because it's not like the model is forced to just take one path. Instead, there's different paths that the generation can go down, right? Because we know that at a given iteration, if we choose a given character like A, right, instead of a character like B, then that is going to affect the future tokens that are generated because they're all conditioned. They're all kind of dependent on the previous tokens that came before it, right? So we can get some more interesting and some more fun outputs if we occasionally choose maybe the slightly less likely token at a given iteration, because then this can allow the model to go down a different path and generate something different. Okay, we're finally ready to jump into the code. Since we're going to be returning a string that's actually going to be growing at every iteration, depending on which characters we generate, first I'm going to declare a variable called result, which is just going to hold the list of generated characters, and then we can just convert this into a string at the end. And again, to maintain the reproducibility here, we actually have to have this generator, which is going to keep track of all the random numbers and make sure that everything's consistent. So you actually have to set the generator to the initial state at every iteration to make sure everything's consistent. If that doesn't make a ton of sense, don't worry, it's not too important. The only thing we really need to do is just have our code here. And we've said that it's going to be some arbitrary number of lines. And then you're going to call torch.multinomial on this line over here, right? Because we know that there's going to be a call to that sampling function at some point. And like we said earlier, we're going to pass in the generator. And then right after that line, we need to set the state again and then finish our code, however many lines that is for the loop, for the body of the loop, and then it starts over again. So the first thing we're going to go ahead and do is check to see if we even need to do any truncation. So has the context grown long enough to where it's longer than context length? And the way that I'm going to do this is since context is b by t, right? So we know context is b by t, and I'm actually going to go ahead and check the length by using the second dimension, right? So an easy way to check the second dimension is just take the length of the transpose version, because len always returns the first dimension, right? If it's b by t, len of context is b, right? But if you actually transpose it, you flip it into a t by b, you could say len of context dot t. So dot t for transpose actually is that t, not to be confusing between those t's. So then if we say, okay, if the length of context dot t, so transpose, is actually greater than the context length, then it's too long and we need to truncate. So we could say context equals context, preserve all the batch dimensions, and we can go ahead and say from context length, so go context length tokens backwards, and then so that's kind of what negative context length means, right? Going context length tokens backwards from the end, and then colon all the way to the end. So then we'll preserve everything from that point onwards. Then based on this context, we need to get the model prediction. So we can say prediction equals model.forward, or again, just use the default calling. So we can pass in context, and this is the truncated context that we passed in. Then we want to focus on the last time step. So you might say last time step, because again, we only care about getting the next token. So prediction, and then we might say colon, -1, colon, as we talked about previously. So instead of this being b by t by v, right, this one is b by t by v, this one is just b by v, which is actually what we wanted. Then we can get our probabilities by calling softmax, so nn.functional.softmax, pass in that last time step, and we want to normalize along the vocabulary dimension, make every row in this tensor actually sum to 1, and all the entries need to be between 0 and 1. So pass in dim equals -1, and now we can actually call torch.multinomial, right? So we can actually go over here. It says now that we have our probabilities, we can call torch.multinomial. So let's go ahead and do that now. We can say next char or next character is torch.multinomial, and we know we need to pass in the probabilities. We know we need to pass in the number of new, essentially how many times do we want to draw out of this bag. So that's called num samples. So you can say num samples equals 1, or you can just directly pass in 1. And then we do have to pass in the generator just to make sure the sampling is consistent. And then we want to set the state just so everything's consistent, but we don't have to touch that at all. And here's where we're going to finish out the loop. We know we need to grow the context and actually append the new character we just got. So we can use torch.cat for that concatenation. So torch.cat, we pass in our tuple that torch.cat expects, and we just want to concatenate context with the new character. So then we can actually say dim equals -1 over here. So that takes it from something that's b by t, that's the initial shape of context, to something that's b by t plus 1. That's what passing in dim equals -1 does over there. We're focusing on this dimension over here. And then we can actually append to res, right? So we can actually say int to char, that's that dictionary that we had earlier, right? We want to index this with whatever token we chose. So we can say next char, and next char is supposed to be like an integer, right? Because the model is thinking in terms of these token IDs, not the literal strings themselves. The model is thinking in terms of the integers that represent each string. However, this is actually going to be a tensor still, since it's actually something that's returned by torch.multinomial. So we can simply do .item, and .item extracts the number out of a tensor of size 1. So if you had a tensor, which is like wrapping around some sort of single constant, and then if you call .item, it gives you like the actual number, the actual scalar. So that would give us 5 over there. And then this is just what we want to append to res. So we can say res.append of whatever that dictionary gave us, whatever character that was. And now we're ready to actually return the string. However, we need to return a string, not a list. So why don't we just join all the entries in the list with essentially the empty string. So we can say return empty string dot join of res, and this is going to join all the elements in the list with the empty string. And we can see that the code works. Next, I highly recommend checking out the linked Google Colab notebook in the description. You don't have to write any more code. In fact, you're going to see your code, this exact generate function that you wrote here, being used in that notebook. And all you have to do is click run on each cell one by one, and you'll actually, every time you run it, you're going to get new Drake lyrics. So that'll be really interesting. She know what she need, all she blessed.